We just learned about molecular geometries and how the shape of the molecule matters. Now, molecular polarity is one of the most important consequences of determining the molecular geometry. So let's look at a diatomic molecule. Here we have HF, hydrogen fluoride, or hydrofluoric acid. A diatomic molecule is polar when the electronegativities of the two atoms are different, which is something we looked at in a previous chapter, where we used our electronegativity table to find the difference in those values. So we would call this a polar covalent bond. Now, we talked about this in previous lessons when we only looked at two atoms, so diatomics, or we were looking at an entire molecule, but only determined the polarity of the individual bonds. Now that we've learned about molecular geometry and how the shape of the molecule is set up in 3 dimensions, we can now apply what we've learned about polarity to the molecule overall. So, the polarity of a molecule, meaning something that is made up of 3 or more atoms, is going to depend on 2 things. First is the polarity of the individual bonds, which is something we've already done in the past. And then it also depends on the molecular geometry itself. How are those bonds arranged, and how does the polarity of those bonds affect the polarity of the molecule overall? So let's look at carbon dioxide. So if we look at first the polarity of the individual bonds, we want to look at carbon to oxygen. So we see that carbon has an electronegativity of 2.5 and oxygen has an electronegativity of 3.5. So the delta En is equal to 1. Remember, when we're calculating the change or the difference in electronegativity, this is an absolute value calculation. We're just looking for the absolute value difference. Because that difference in electronegativities is 0.1, this falls into the second category of being a polar bond. So the bonds in each, for both carbon and oxygen double bonds here, are both polar. Okay, and our more electronegative atom is oxygen, so the electrons are being pulled towards the oxygen, which we denote by an arrow. So the electrons are being pulled towards both oxygens away from the carbon. So now that we know that the bonds are polar, we want to look at the molecular geometry overall to determine if the molecule is polar. Now, we can have molecules that have polar bonds but are overall nonpolar because we have to think about how the molecule is set up. So I'm going to erase our little notation here so we can easily see this. So our electrons are being pulled in carbon dioxide in equal but opposite directions. Okay, these are both oxygens, so they're both being pulled towards the oxygens with equal amounts because the difference in electronegativities for both of these is 1.0. So if we think about symmetry and geometry, if I were to draw a line right down the center, these would be equal on either sides. So the polarity of those bonds cancel each other out. It's like playing tug of war. The electrons are being pulled this way and this way, but with equal strength. So no one's going to win that tug of war. So overall, this molecule is nonpolar. Okay, now if we think back to when we talked about polarity, we said that we could see where electrons were localized on polar molecules. In this one, there's no one spot, in this molecule I should say, there is no one spot that has more electrons than the other. We have high electron density on the oxygens and not a lot on the carbon, so they equal each other out. There's no one spot that we can point to and say that portion has more electrons than another, and it is being shared unequally. So because the electrons are being shared equally and being pulled in equal but opposite directions, the molecule overall is going to be polar. So our final statement here is that the bonds in CO2 are polar, but the molecule overall is nonpolar. Okay, let's keep looking at this. So for our little review here, I have the molecule CH4, which is methane, and we want to know, are the bonds in the molecule below polar, nonpolar, or ionic? Well, we know it's not going to be ionic. We're going to cancel that one out because we have bonds. If we have bonds and we know that we're between a metal or two nonmetals, then it can't be an ionic compound. So we're really looking for, are the bonds in this molecule polar or nonpolar? So we're just going to get rid of that ionic option. It's not going to be ionic if there are bonds. Okay, so let's determine that. So we're looking strictly at the bonds. Since all of the bonds are the same, they're all CH bonds, we just have to look at the delta En of carbon and hydrogen. So carbon's electronegativity is 2.5. There it is on our chart. And hydrogen's is 2.1. There it is on our chart. So that's a difference of 0.4. That falls into our first category. So the bond, the actual bond itself, is going to be nonpolar. Okay, because the electronegativity difference is less than 0.5, the bond itself is nonpolar. Now we're going to take it one step further and say, is the molecule overall polar, nonpolar, or ionic? Well, again, it's not going to be ionic at all. Goodbye. Okay, so is the molecule polar or nonpolar? Well, we said that these are all nonpolar bonds, so it's not like the electrons are being pulled in any way. So they're being shared equally in all of these bonds, and all of those bonds are equal. Okay, we have symmetry, right? I have a line of symmetry here, a line of symmetry there, a line of symmetry there, a line of symmetry there. So because this molecule is symmetric, it is going to be nonpolar. Also, I can't have a polar molecule if it's made up of nonpolar bonds. Oops, I spelled molecule wrong. Okay, so because all of my bonds are nonpolar, the molecule overall is nonpolar. It's also very symmetric, suggesting that it's also nonpolar. Okay, let's look at our next one. So again, to review, are the bonds in this molecule polar, nonpolar, or ionic? We're going to get rid of ionic. We know it's not an ionic compound. It's water. Water is not ionic. So we want to look at the delta En of oxygen and hydrogen. Okay, so we're looking at this bond here. So oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So that's a difference of 1.4. Okay, so that falls into our second category, meaning that this bond and this bond are both polar. Okay, let's look at the molecule overall. So if these bonds are polar, the electrons are being pulled up towards that oxygen. Okay, so because they're being pulled and they're not being pulled in equal and opposite directions, they add together. Okay, so the molecule overall is going to be polar as well. If you think about it, let's try to draw some here. Should I use a highlighter? That might be easier. We'll say that blue is low electrons, and red is high electrons. So because the oxygen is pulling all of those electrons towards it, it has a lot of electrons over here. Okay? The hydrogen only has one electron to give away, so if the bond is being pulled, or if the electrons through that bond are being pulled towards the oxygen, that creates area down here by the hydrogens where I have essentially no electrons. So this gives me an area of partial positive, right? Because there's little to no electrons there, so it's partial positive, and an area of partial negative. So if I have an area of partial positive and partial negative, that means that we have an overall polar molecule. Okay. Also, if you think about it from symmetry, there's only one line of symmetry there, and those arrows don't necessarily cancel out. I can't draw a line of symmetry there, I can't draw a line of symmetry there or there, so this molecule is not very symmetric, meaning that it's going to be polar. Okay, in our final example, let's determine if the bonds in BCl3 are polar, nonpolar, or ionic. Well, we have bonds, so it's not ionic at all. So we have polar and nonpolar to determine. So let's look at the delta En. Boron is 2.0. Chlorine is 3.0. Again, this is an absolute value, so that gives us a difference of 1.0. That lands us in our second option here, which says that it is polar, so the bonds are polar. Chlorine is our more electronegative molecule, so they're being pulled towards that chlorine. Okay, so now let's determine if the molecule is polar or nonpolar. So we said that the electrons are being pulled towards the chlorines. Okay. So if we again go with our highlighting, we have areas of more negative spots here and here. And we have an area of more positive there. Now if we look at this, this is a symmetric molecule, right? There's a line of symmetry, there's a line of symmetry, and there's a line of symmetry. And you can also think of these arrows as being pulled in equal but opposite directions. They're all being pulled towards chlorines, but those chlorines are all 120 degrees from each other. Okay, we know our angle from our shape, okay, our molecular geometry. So overall, this molecule is nonpolar. So we can have nonpolar molecules made up of polar bonds. Okay, because what can happen is those polar bonds can all cancel out. That's what we saw in carbon dioxide, and that's what we're seeing here in BCl3. Okay, so let's look at another example of this. This uses vector math. If you're familiar with vector math, maybe that's the best way for you to understand this. If not, you could just look at how the arrows kind of are being pulled, or we can look at electron densities. That's totally fine. There's many ways to visualize this. So my first example, I have CCl3. These are all polar bonds, and again, they're being pulled towards the chlorine, okay, just like our previous example. So we have 4 spots of high electron density and 1 spot of low electron density. Now because this is tetrahedral, all of those bonds are being pulled at 109 degrees from each other. So they're going in equal but opposite directions. I can't really show lines of symmetry here because we're now in 3 dimensions, but you could have a line of symmetry on this plane, and then I can't draw the other plane very well, but there's a few planes of symmetry in this molecule. So overall, this molecule has polar bonds, but the molecule itself is nonpolar. So another example of molecules that have polar bonds overall being nonpolar. If I were to take one of these chlorines and replace it with a hydrogen, well, that changes how the electrons are being pulled. So that carbon-hydrogen bond is now, the carbon is more electronegative than the hydrogen, so the electrons are now being pulled from the hydrogen to the carbon. So if you were to highlight this, we have our electron density focused here on the chlorines and slightly on this carbon, okay? And then we have an area of very positive portions up here where that hydrogen is. So we see an uneven pull of electrons where the electrons are mainly down here with a partial negative. They're focused really down at that bottom, that trigonal base of the tetrahedron. And then there's an area of partial positive right at the top there, okay, because of that hydrogen. So the bonds in this molecule are polar, okay? The carbon-chlorine bonds are polar, the carbon-hydrogen bond is not, okay? And the molecule itself is also polar, okay? So if we have uneven distribution of atoms, maybe they have differing electronegativities, then we're most likely going to have a polar molecule itself. So let's keep practicing. For the following molecules, determine if they are polar or nonpolar, and if they are polar, determine which atom is the most electronegative. Okay, so the first thing we have to do is draw the structure. Okay, so we have to draw our structure for each of these. So for time purposes, I'm just going to draw the Lewis structures. If you need time to draw these Lewis structures with me, feel free to pause the video and use your Lewis structure guidelines to help you along and make sure that your Lewis structures match mine. So here we have carbon, we have a double bonded oxygen and 2 hydrogens. Okay. We then have N2. I'm going to draw the Lewis structures first and then determine our electronegativity difference. So we have N2. This is going to be N triple bond N, and then there's going to be 2. A lone pair on each nitrogen. SiH4. Again, I'm trying to draw these with semi-accurate looking structures, so they kind of look more like our geometries rather than a 90-degree Lewis structure. And then we have OCS, which we've drawn in the past, and that is oxygen with a double bonded carbon with a double bonded sulfur. Okay, you can have other variations of this, like oxygen single bonded carbon, triple bonded sulfur. You could have multiple different versions of it, but because polarity of bonds is not affected by if it's a double or a single or a triple bond, you can draw it anyway and your answer will still be the same. So let's look at some electronegativities. Because I don't have my electronegativity chart here, I'm just going to write these out. Carbon is 2.5, oxygen is 3.5, hydrogen is 2.1, nitrogen is 3.0, silicon is 1.8, and sulfur is 2.5. Okay, so for our carbon-hydrogen, that's going to be 2.5 minus 2.1. Let me zoom in so we're looking at one structure at a time. So we have 2.5 minus 2.1, so that's 0.4. 0.4, so that's going to be 2 nonpolar bonds, and then our carbon-oxygen, so carbon's 2.5, oxygen's 3.5, that's going to be a 1.0 difference. Okay, we determined that when we did carbon dioxide. Okay, so there's some lone pairs on that oxygen there. So this molecule has an area of more positive and more negative because it's polar in that respect. So this is a polar molecule, and they're being pulled towards the oxygen, which is the most electronegative. Okay, Let's look at N2. Now we said when we talked about polarity of bonds, if it's the same atom, it has an electronegativity difference of 0 because you're basically taking 3.0 minus 3.0. That's our electronegativity of nitrogen. So this has an electronegativity difference of 0. So the bond is nonpolar, which means that the molecule itself is nonpolar. Okay. Next we have silicon and hydrogen. They're all the same. So silicon is 1.8 and hydrogen is 2.1. So that's a difference of 0.3. So these are nonpolar. And since they're all the same, the molecule itself is nonpolar. Okay, there's no one area of more electron density than the other. The electrons are all being shared equally in all 4 bonds. Okay, and finally we have OCS. So let's see, carbon, oxygen, that one is 3.5 minus 2.5. So that's an electronegativity difference of 1.0. The carbon sulfur is 2.5 minus 2.5. So that's an electronegativity difference of 0. So we have a polar bond and a nonpolar bond. So our electrons are being pulled towards this oxygen and being pulled away from that sulfur. So we create a partial negative and a partial positive area. So this is a polar molecule. And our more electronegative atom is oxygen. Okay, so we have the electrons being pulled this way. They're being essentially shared in that carbon-sulfur bond. So our electrons are just being pulled towards that oxygen, creating a polar molecule. Okay. Let's do a little bit more practice. So this is so that we can start to visualize our individual kind of molecules and how things are being pulled. Is it symmetric? Is it non-symmetric? Things like that. So which of these molecules are polar? And you should assume that all of these bonds are polar. So that's a polar bond. All of these bonds are polar. Okay, so take a second and pause the video. Think about this problem. Think about which ones are going to be polar or non-polar and why. Okay, so I think our most obvious one that of being polar is going to be this one, because it is the least symmetric out of all of the other atoms or molecules. So if we think about it, if these are polar bonds, we don't know which one is more non-polar, but we can assume maybe the larger of the two atoms are going to be the more polar or more electronegative atom. So we know that we have some portion up here that the electrons are being pulled towards that's going to be more negative, and some portions that are going to be more positive. Now this could be reversed. This could be that, you know, the blue ones are more electronegative, so the electrons are being pulled this way, and that there's more of a positive on that central atom. But either way, it still shows that there's an unequal sharing of the electrons, creating a polar molecule. These other three examples, since we don't know the exact identities, we don't know the magnitude of their polar bonds, so we really only have their symmetry to look at. If we knew the magnitude of how polar the bonds are, we could tell if there's more of a electron density on one atom or the other, but since we don't know that, let's just see if there's symmetry in these atoms. Well, we know linear molecules are symmetric down the middle, so those two polar bonds are going to cancel out. So these are polar bonds with a non-polar molecule. Okay. This second one here, it has all the greens are in the same plane being pulled at 90 degrees from each other, so those essentially cancel each other out. And then the two red atoms cancel each other out as well, because they're being pulled in equal but opposite directions. So because all of those atoms, their polarities essentially cancel out, this is also a non-polar molecule. Okay, so that's also basing it off of their symmetries. In this last one, this is a tetrahedral molecule, so there is symmetry within that. Okay, again, we don't know the exact magnitudes of these atoms and their electronegativities, so we can't say if these white ones have more electronegative pull or not for there to be a more polar portion. Okay, so there could be, if we knew that, there could be an area that's more negative versus an area that's more positive, but you would need to know the identities to do that. So basing this strictly off of symmetry, this is a symmetric molecule, meaning that this would be nonpolar.